Okay, so to start with, we're going to take a look at what it means, the word ionisation. And so we can think about this in terms of chemistry, what it means to be an ion. However, actually, if we think back to physics GCSE, their definition of ionisation is, when we looked at radioactivity, is actually closer to what it means for ionisation in this context. As in chemistry, when we think about ions, we can think about cations and anions, so positive and negative ions. However, in GCSE physics, when we talked about ionising radiation, so your alpha, beta, gamma radiation, causing ionisation of atoms, what we talked about there was the radiation removing an electron from the atom. And in this case, it's the same thing. So ionization energy is referring to our energy to remove an electron. However, we need to be really specific with our terminology. And the way to think about our terminology here is to think about what's actually happening. So here we've got an atom X in the gaseous state, and it's forming positive ion, and one electron has been removed. Our definition here is that it's the energy required to remove 1 mole of the most loosely held electrons, i.e. outer shell, from 1 mole of gaseous atoms to produce 1 mole of gaseous ions with a charge of +1. And so our units for ionisation energies are often given in kilojoules per mole. So it's really important that when we're defining it, we're talking about 1 mole of electrons from 1 mole of atoms to produce 1 mole of ions with a +1 charge. Now there are various factors which can affect the size of our ionisation energy. So the distance of the outer electron from the nucleus. So here, the greater the distance of the outer electron, we have a weaker attraction of the outer electron to the positive nucleus, and therefore it is easier to remove the electron, and therefore lower ionisation energy. At GCSE we looked at the reactivity of group 1, and in order for group 1 metals to react they had to lose an electron, and here we're talking about the energy required to remove an electron. So there we looked at going down the group, our group 1 metals became more reactive, and that's because the outer electron became further away from the nucleus, and so it became easier to remove the electron for them to form positive ion. And so the same thing can be applied here to ionisation energy. A second factor to look at is nuclear charge, which is affected by the number of protons. So the greater the nuclear charge, i.e. more protons, so higher positive charge of the nucleus means there's going to be a greater attraction of the outer shell electron to the positive nucleus, and therefore it's going to be harder to remove the electron, and so we're going to have a higher ionization energy. And then the third factor which will affect our ionization energy is shielding. So this is where there are shells of electrons between the nucleus and outer electron, which shields the effect of the positive nucleus, so then you have a weaker attraction. So more shells of electrons means more shielding, which means a weaker attraction, and therefore easier to remove electron, and so we have a lower ionization energy. So then when it comes to our periodic table, we can look at our trends going across the period, and we see that generally our ionization energies increase across the period. However, going down a group, it decreases. So we need to think about what's happening across a period. So across the period, going, say for example, from lithium to fluorine. Now they're in the same period, so they have the same number of shells. Therefore our shielding is approximately the same. However, what has happened is we have increased our nuclear charge as we have more protons, and we've also decreased our distance of the outer electron from nucleus, and so a combination of these factors therefore causes it to increase. Same shielding, so it doesn't really have an effect. That increased nuclear charge makes it harder to remove the electrons, and again a decreased distance from the outer of the outer shell from the nucleus again makes it harder, and therefore we've got an increase in our ionization energy. Going down our group, we have increased our shielding as we've got more shells. We've also increased the distance of the outer shell from the nucleus, and therefore both of these makes it easier to remove the electrons, and so we have decreased our ionization energy. So of course there are exceptions to our trend. So exceptions across the period are the ones we need to know about. And in order to do that, we need to start thinking about electron configuration. So remembering that our energy levels, we have S and then 3 p orbitals from our energy level 2 upwards. So 1 is only S, but energy level 2, you have 2 s orbitals and also the 3 p orbitals. So the first, say, dip in our trend, so instead of an increase in our ionization energy, we actually get a decrease. And we see this for our group 3. So group 3, we're going to have an NS2 NP1 configuration. On ionization, this becomes NS2. And so what's happened is we've had removal of an electron from the p orbital, which is higher in energy than s orbitals, and if it's higher in energy, that means that it's going to be easier to remove. As remember, our electron shells are energy levels, so the further out the shells they are, the higher in energy they are, and therefore the less energy is required to remove them from the atom. And so we have a lower ionization energy than expected. So we're comparing this to our group 2, where we're going from NS2 to NS1. So it's a lot easier to remove from the p orbital, which is higher in energy, than from the s orbital, which is lower in energy, and therefore we have to put in more energy to remove it upwards. Our p orbital is that slightly bit higher in energy, and so requires less energy in order to remove. We also have a dip for group 6. So here we're going from an NS2 NP4 configuration to an NS2 NP3 configuration. And here I often like to do this with boxes. So each box, remember, can have 2 electrons, each box representing an orbital. So this is my NS and this will be my NP orbitals. So if I've got 4, they originally singularly occupy, but that 4th one of the orbitals must be doubly occupied. And so here we have electron repulsion, so electron pair repulsion in the p orbital, whereas on ionization our configuration becomes this, and so we no longer have that electron pair repulsion. So removal of an electron from a p orbital where there are paired electrons. This is easier to remove, and so we have a lower ionization energy. So it's easier because our electron-electron repulsion between those paired electrons is removed. The final thing I want to talk about is our second ionization energy. So this, if we think about process, we've already done one, so we're starting out with a mole of gaseous ions with a +1 charge. To remove another electron, we're then going to be forming a 2+ ion and a mole of electrons separated. So here it's the energy to remove 1 mole of electrons from 1 mole of gaseous ions with a +1 charge to form 1 mole of gaseous ions with a +2 charge. This second ionization energy must be greater than our first ionization energy. And this is because we are removing electrons from a positive ion. So that electron is going to be strongly attracted to the positive ion, and so it's going to take more energy in order to do that. Okay, so to recap what we have covered, so what is meant by the term ionization energy. We've also looked at the general equation for first ionization of an atom. So we could say, what is the general equation for ionization of an atom? Then we've looked at how does the distance of the outer shell electron from the nucleus affect the ionization energy. How does the nuclear charge of an atom affect the ionization energy? How does shielding affect the ionization energy? And then, what is the general trend in ionization energy across a period? And what is the general trend in ionization energy down a group? Why is NS2 NP1 to NS2 an exception? NS2 NP4 to NS2 NP3, an exception. And then of course we also looked at Y is the second ionization energy,